let's get started. So I'll begin by defining the graph model that I'm interested in. So I'm going to say that a graph G is a sample from the model. There are a bunch of parameters which will be explained later. So G is going to be a sample from the two community Gaussian mixture block model. If we sample it as follows. So the first step is you sample n vectors, u1 through un, IID from a mixture of spherical Gaussians, so a mixture of two spherical Gaussians. So I'm going to have half times the normal distribution centered at minus mu times, without loss of generality, let's just take the indicator vector in the direction of 1, the first coordinate, and I'll have spherical covariance plus half times the normal distribution centered at the same point reflected across the origin. So at mu times the first coordinate indicator with identity covariance as well. Thinking about these as distributions over d-dimensional space. Okay, so we've already explained the first two parameters we have. N is the number of vertices. D is the dimension that the Gaussian mixture lives in. Question already? Can I write bigger? I can try. You can also sit a little bit closer. There's a lot of space in the front rows. Okay, so the first thing that I do is I sample n points from this mixture of two Gaussians. Okay, and the second thing that I do is I add an edge, ij, to the edge set of G, if and only if the vectors ui and uj have inner product which exceeds some threshold tau. And what I'm going to do is I'm going to choose this tau in advance, right? So like it's a parameter of this model. So tau is chosen so that the marginal probability of each edge is p. So let me draw a picture as well, right? So what we're going to do is we're going to start with a mixture of two Gaussians, one centered at minus mu and one centered at mu. Okay, I'm going to sample n points using Sam's fancy colored chalk that he gave me from the mixture. And then for every pair of points that's close enough together that have sufficiently high inner product, I'm going to add an edge between them. Okay, so maybe it'll look something like this. This is going to give me the graph. And then I'm actually not going to observe the embedding at all. Hopefully that's clear. Right, so this whole embedding step is kind of in a black box, which I don't get to observe. I only observe whatever the resulting graph looks like. So let me try to draw it in such a way that makes it clear. Okay, and this picture is a two-dimensional drawings, but really this is all happening in d dimensions. All right, is the model clear? Okay, so the point of this model is supposed to be that we think of networks that we observe in real life as having every node has some kind of feature vector that is latent that we don't observe necessarily. Maybe we have a little bit of information about it, but often we don't. Okay, so there's some kind of latent feature embedding for our network that we don't know, but the idea is that vectors that have, or the points, nodes that correspond to similar feature vectors should be more likely to be connected. Okay, so that's where this model comes from. The idea is that each of the mixture components corresponds to a distribution over features for a specific community, let's say, in the network. Okay, and now I'm going to observe a mixture of points from this, like, different individuals drawn from these networks. Then I only observe the connectivity information. So that's supposed to be the idea. And I guess that, maybe it's useful to contrast this with the stochastic block model. So, okay, compared to the stochastic block model. So the stochastic block model is a different model for social networks. Here is the simplest two-community version of the stochastic block model. Basically what you have is you've got roughly n over 2 vertices which have the red label. And you're going to have n over 2 vertices which have the blue label. Okay, and every edge between vertices of the same community is present independently with probability p. And edges across communities are present independently with probability q. And we like to think of q as being smaller than p, typically. This is like what models a community reasonably well. Okay, but the point is that here, the edges are sampled independently, and there's no notion of a latent embedding. Okay, so this is the stochastic block model, and it's a model that has received a ton of mathematical study, and a lot of, including by many people in this room, and we've managed to prove, well, I haven't proven anything about it, but people have managed to prove many, many beautiful things about the stochastic block model. But I would argue that the stochastic block model does not capture the features of real networks as well as the Gaussian mixture block model does. I mean, even this is a pretty stylized model, but it comes closer to capturing properties of real networks that we see today. So I think, you know, it would be nice if we can understand this model better, because it's still mathematically tractable. Hopefully we can use it as a sandbox to study algorithms for clustering, et cetera, and maybe learn things that are more useful in real algorithms as well. Yeah. David? Yeah, so I think if you hold n fixed and you send d to infinity, you do get that this is basically like the stochastic block model, although I haven't checked this, but I think that is true. And you would need to choose, well, I guess you can choose tau to scale as a function of mu, but yeah, so I guess like you can compare, okay, so in the stochastic block model there are usually, I guess, a couple of parameters that matter. So one is the number of vertices, another is the average degree, and there's also the separation between p and q, right? And then here there's yet another parameter, the dimension, okay? And probably you would have to make sure that everything interacts in the right way in order to have this limiting statement be true. Yeah. Okay. Excellent. Okay, so the Gaussian mixture block model or variants thereof has been studied before a little bit. So let me just list a couple of the references to make sure that you know where to look. Okay, so I'll list a couple of works. So one work is the work of Abe, Sarah. I never know if I'm pronouncing Enrique's name correctly. Did I do okay, Guy? Bosch. All right. And Raleigh and Sandin. So this is from 2020. And another pair of works by Galotra, Mazumdar, Paul, and Saha, one from 2018 and one from 2020. So these works they're not exactly in the Gaussian mixture block model, but they're in some kind of spherical, like separated sphere version of the same model. But these works are mostly focusing on the situation where the dimension is fixed and n is going to infinity. So I think in particular this first work only focuses on the situation where d is equal to 2. In the second work, at first in 2018, they only studied the case where the dimension was 2. And then in 2020, they allowed the dimension to be higher, possibly as high as logarithmic in n, but certainly no higher than that. So this is kind of the prior work in this model. And then there are also other works that kind of study other geometries, right? So again, motivated by this idea that there should be some feature space that's associated with a vector, there are kind of other settings. Like one situation is the mixed membership block model. And people have studied this kind of community structure on the torus. And also, I guess, Dan and Ronen, Eldan, and Hester Peters have a work where there's not really two communities, but instead you consider just this one sphere, right, and think of that as your community model. Okay, so. But I guess basically what my point here is that there are other geometries, and I guess you can decide if you think that these are convincing models for communities relative to this one. And prior work in this kind of model has mostly considered the low-dimensional regime, where the dimension is fixed. And our goal is going to be to focus on the high-dimensional regime. So we're going to be thinking of d going to infinity as n goes to infinity, which seems to be, in some cases, a better model for what's actually going on in the networks that we observe, right? We tend to think of having really large networks, but the feature vectors that we associate with each node should have dimension which is comparable or scaling with the size of the network, rather than thinking of it as a fixed constant. Okay, and there are kind of a couple of goals, algorithmic goals, that we could hope to have given a sample from this model. So our goals, I'll articulate 3 of them. So the first goal we could have is hypothesis testing. Our null hypothesis would be that actually we're observing a graph which was generated not from a 2-community mixture model, but from a 1-community mixture model. So the null hypothesis is that the separation mu between the means is actually 0. This is equivalent to saying that there was only 1 community all along. And our alternate hypothesis is going to be that mu is at least some value epsilon, bounded away from 0. Okay, so this is analogous to the hypothesis testing question in the stochastic block model. We can try to study it here as well. Okay, slightly more sophisticated algorithmic question is whether we can do clustering in this model, right? So the second question is clustering. Here the goal is to partition the vertex set into the union of 2 partitions, S1 and S2, so that the overlap of S1 with the set of points that came from the first component, so I'm just going to call this C1, okay, really I don't care whether it was C1 or C2, hopefully that's clear. I want this to have size roughly n over 2. So let's say that I want this to be 1 plus or minus little o1 times n over 2. This is like strong but not exact recovery in the stochastic block model, right? So I want to correctly label, n over 2 roughly fraction of the, or like close to 1 fraction of the points. And you could, you could formulate different goals like exact recovery or weak recovery, et cetera. But we didn't do that in this case because, we're just making a preliminary study. So, okay, and then thirdly, this is a goal that we don't necessarily associate with the stochastic block model because it doesn't make sense. The third goal is to embed. Right, so remember in the end, we're only observing the graph. We don't know what its latent embedding is like. Right, and a reasonable goal is to say, I know that this graph was generated by, sampling points from d-dimensional space. Let me map every vertex to a point in d-dimensional space so that the mapping is close to the original embedding that was used to generate the graph. So I'm kind of trying to recover this latent embedding. So here the goal is to find vectors u hat 1 through u hat n. And because these embeddings are only going to be unique up to rotation, a reasonable goal that I would have is to have that if I look at the expectation over a pair of vectors corresponding to different vertices, and I look at the difference between the inner products of my approximate embedding vectors u hat I and u hat j, and the inner product of the true vectors ui and uj, this in absolute value is at most little o1 times the expected inner product of the true embedding. Does this make sense? So I'm just trying to recover an embedding which is, unique. This embedding is only unique up to rotation. I'm doing my best to recover an embedding up to rotation. So these are going to be our 3 algorithmic goals. Okay, any questions about the setup? Yeah, in the back. No, not necessarily. So I'm going to consider, basically my goal was to characterize the entire regime of D scaling with n, and you will see that I have fallen short of this goal, but D and n are not necessarily scaling like a constant factor of each other. Maybe I'll say a couple of things. So I'm about to state the main theorem, but before I do this, let me try to kind of warm us up by trying to understand which problems should be hard as which parameters change. Okay? So for hypothesis testing and clustering, I guess it's pretty clear that as the separation between the components grows, the difference between the communities grows, and the problem should become easier and easier. So mu large implies it's easier. Similarly, as the marginal edge probability grows, right, I'm seeing more and more information about the underlying embedding expressed in the graph itself, right? So you can think if this graph is super, super sparse, right, if p is set so small that I don't see any edges, then obviously this task is impossible, right? And then as p gets larger and larger, let's say up until p takes value half, the problem gets easier and easier, right? So p large implies that the problem gets easier. It's not so clear how dimension should interact with the tasks of, clustering and hypothesis testing. I mean, as I guess David had some intuition about this coming in earlier, but if the dimension goes to infinity much faster than the number of vertices, then somehow we are losing the geometric structure and we approach the stochastic block model. But one thing that seems pretty clear is that as the dimension gets larger, embedding should become harder. Okay, so D large implies embedding is harder. Because, we're seeing only n points in D dimension. So if D is really big compared to n, then how can we hope to embed back into D-dimensional space? Okay, so given this warm-up, I'm ready to state our main theorems, but I'm going to do it in the form of a picture, mostly a picture. Okay, so when the dimension is sandwiched below by some polylogarithmic in n factor and above by np, the average degree, divided by polylog n, then with high probability, a very naive spectral algorithm, which I will describe to you in a second, can do all three tasks. Okay, but each task, it requires a different requirement about how large the separation will be. So this is the picture part. So here, if on the x-axis, I've got the separation mu growing, then embedding is actually possible all the way through. Something weird is going to happen at 1 over d to the 1/4, but let's pause before discussing this. So this is embedding. So embedding is always possible. Clustering becomes possible around when mu becomes like 1 over d to the 1/2. And then hypothesis testing becomes possible at a lower separation, which I guess is consistent with intuition, because testing should be easier than clustering. Right, so hypothesis testing becomes possible at, okay, this number 1 over npd all to the 1/4. So this is what we're able to show. Okay, so I will pause for a second and let you guys ask questions, then I will make a couple of additional comments on these results. So any questions? Yeah. Yeah, excellent question. Okay, so in some cases, I think the answer is yes in all three cases, but I can formally show that that is the case for clustering. Okay, also just keep in mind that here everything is like fuzzy up to polylogarithmic factors, right? So here, like really, this blue line starts polylog above this, and the lower bound is going to start polylog, or like exactly at this threshold, okay? But so let me draw a little, let's draw little red X's to show that something is not possible. So it is not possible to cluster information theoretically when the separation is below 1 over d to the 1/2. And the lower bound actually comes from the clustering lower bound in the Gaussian mixture model before I discretize it to a graph. Okay, so up to polylogarithmic factors, the moment that clustering was even possible in the mixture model to begin with, it is also possible in this discretized version. Okay, like provided that we're satisfying these constraints, right? That the dimension is not too large relative to the average degree, and also this introduces a lower bound on the average degree. So I think this is kind of remarkable. Like going into it, I sort of expected that you would, because when you discretize, it seems like you should lose a lot of information. Okay, but here it doesn't seem like we're losing that much information. Although you could zoom in on this point here and you could ask, are you losing information at all? We didn't answer the question precisely enough to answer this question. For testing, we can prove a lower bound. Okay, it doesn't match all the way the lower bound. I forget even where it is here. But I think this lower bound that we proved, it was like pretty easy, and it shouldn't be tight. I think if we worked harder, we could prove that this lower bound matched the testing lower bound, and that this is this naive spectral algorithm in this parameter regime succeeds whenever it's information theoretically possible to hypothesis test. Yeah.
So I'm wondering, so here you've stated the parameters in terms of like the separation and other properties, right? So I could also try and directly compare it to the plain vanilla stochastic block model.
Yes.
In the same way that there's a function, there's a a that's
right,
a
right,
function of all
right,
the parameters
right.
that describes the inter.
Yeah, like you want to know what is the P and the Q.
Right, exactly. So they'll be dependent inside the cluster for sure. But I'm just wondering from like an intuition standpoint, like where, how does the stochastic block model picture map onto this? Because it seems like one difference already is like testing and clustering look asymptotically different. Whereas,
well, okay. Hold on a second. Yeah. Let's realize for a second that I am automatically in a situation where the dimension, like where the average degree has to be, growing with n, right? Sure. So I'm not like near the KS threshold. Sure. Okay.
Yeah. But even there, these
right.
would be off by much more than polylog factors.
True. Yeah. True. Right. Unfortunately, I wish, this is an excellent question, and I wish that I had thought about it before you asked so that I could give you a good answer right now. But I didn't actually bother to do the comparison. It's a little bit annoying. But I will think about it, and I'll try to answer later. Okay. Yeah, Guy.
I guess another question related to what you mentioned before about the thresholding not reducing the information. This is sort of a large P regime where P is bigger than P over n. Is there some significance in P over n, some intuition for, like, P is this big, then you're not losing information?
Yes. Okay, so I had planned to, say this at the end, but I think I might as well say it now since you asked this great question. So Guy's question is like, what's up with this d less than np? Why is this significant? So here's like an aside. So in a moment I'll say more, but here what I said is that a naive spectral algorithm would be able to do all three. Okay, this naive spectral algorithm, basically what it's going to do is it's going to take the spectral embedding that the adjacency matrix suggests. Okay, and the problem is, and the thing that the reason that this all works is that the spectral embedding is going to coincide really, really well with the latent embedding. Okay, but when d exceeds n times the binary entropy of p. So this is like n times p when p is large, or if p is like a constant over n, and this is like np log 1 over p. Then the embedding u1 through un is far from unique. Okay, this is based on work in progress, so take it all with a grain of salt, but I'm quite confident that this is true. I can even explain this to you. If you're interested offline, there's like a really clean reason to see why this might be the case. But yeah, so the point is that when the dimension exceeds n times the binary entropy of p, it's the case that the posterior over embeddings is extremely anti-concentrated. And there are many, many different possible embeddings that could have produced the same graph. And therefore, I think that it may be that some algorithm will work, but the naive spectral algorithm certainly won't work, right? You might be able to do something else with non-spectral techniques. And I think that's a pretty interesting question. Can you do something that circumvents the spectral techniques that still works when the dimension is large? Because as Guy probably knows, but maybe no one else in the room does, so another aside is that if d is going to infinity as n is fixed, we quote-unquote lose the geometry. In the sense that the edges become effectively independent, but the conjectured regime for where the geometry is lost is actually that, okay, my conjectured regime is that D should be bigger than n times the binary entropy of P cubed for this to happen. Okay? So there could be, I mean, there's this pretty wide window, seemingly, where it would be possible to use algorithms that make use of the geometry in order to cluster or test or maybe even embed. But the naive spectral algorithm isn't the right thing to do. And the question is there something that's right to do? Is there an information computation gap? I don't know. I think it's pretty exciting question. Okay.
What does it mean? Like, if I take mu really big, won't there still be something going on? I mean,
Yeah. Okay. Okay. Awesome. So another thing. So why? Okay. So here at 1 over d to the 1/4, you see that I made this little hop in some of the algorithms. All right. In my imagination, I was going to do a little calculation for you, but I think it's actually going to be boring. So just take my word for it that when mu grows bigger than 1 over d to the 1/4, what you end up seeing is you just end up seeing like somehow the separation between the mixtures overwhelms the distance between, like, so the distance between most components will be totally explained by the separation between the mixtures, in the sense that, you know, now like the edge probability will be completely decided by, or almost completely decided by which component you belong to. So above this line, basically what you see is you see a disconnected graph with one component corresponding to the red component of the mixture and another one corresponding to the blue component of the mixture. So like we can't actually, like our algorithms, we can't analyze them all the way up to this threshold because, you know, things become a little bit poorly behaved over here. I think that's like our own laziness rather than like that the spectral algorithms don't work up to here. But above here, like everything is pretty much trivially easy just because you see a disconnected graph. Okay, so embedding might not be easy, but at least, I mean, in the higher dimensional case, embedding might not be easy, but at least clustering and testing should be quite easy there. Yeah, Bryce.
So on this last point about losing geometry, seems like this testing problem looks a lot like the problem of testing between red and graph.
Yeah, definitely.
Is there any formal connection here?
I guess that if you had the separation 0, then they are pretty formally connected.
Right. Maybe in the sense of like a reduction or something?
Maybe even in the sense of reduction. Yeah, but I haven't thought about it that much. Yeah. Okay. All right. Great questions. Maybe I guess I have a couple more minutes, maybe like 5 more minutes. So, okay, maybe I'll just say, I'll at least say what the algorithm is.
You started late. You could have 7 or 8 minutes.
Oh, 7 or 8 minutes. Okay, so okay. So my plan is going to be to tell you what the algorithm is, to give a sketch of why the spectral embedding might be successful. I'll tell you maybe 2 words about our proof techniques, but no more than that, and then I'll give a couple of open questions. Okay, so the algorithm is basically as follows. Okay, so it's the most vanilla spectral clustering you could ever imagine. I take the adjacency matrix. It's an n by n matrix defined so that the ijth entry is just the indicator that the edge ij exists in the graph. Okay, then what I'm going to do is I'm going to take, so the step 1 is compute the eigendecomposition. Of A. Okay, and then in step 2, depending on which goal I had, I will use a different procedure. Okay, so for hypothesis testing, what I'm going to do is I'm just going to reject the null if the second eigenvalue is bigger than some threshold that I chose in advanced data. Okay, the idea being that when there are actually two communities, this will result in a partition of the graph that is spectrally sparse enough that the second eigenvalue will be large. Okay, so classic spectral clustering idea. For clustering, I'm just going to use the second eigenvector. So I just let S1 be the set of all I, so that the second eigenvector's ith coordinate is greater than 0. Okay, right, so I'm doing projection according to the second eigenvector, and it's a 1D projection according to the second eigenvector, and I'm just cutting at the origin. Yeah.
When you say second eigenvalue, second eigenvector, you mean like in absolute values?
No, okay, so I have that lambda 1 is bigger than lambda 2, bigger than lambda 3.
Oh, so you're saying that in the null case, all the eigenvalues beyond the first one will be negative?
This isn't a 0, which is probably really confusing. Yeah, sorry about my handwriting. This is like a theta. I think I only made it worse. Let's pick a different letter. T. Yeah, okay. Okay, yeah, right, so testing, I just threshold on the second eigenvalue. Clustering, I embed according to the second eigenvector, and I make a cut. And then for embedding, I just take the spectral embedding defined by eigenvectors 2 through d plus 1. Right, so what this means is like I would take the n by d matrix where in the ith column I put the I plus first eigenvector. This is just because the first eigenvector is just going to be something related to the degrees of the eigenvector, essentially trash, right, because of concentration of degrees. And then what I'm going to do is I'm just going to take u hat j to be equal to the jth row of this n by d matrix. Okay, so vanilla spectral clustering. Okay, maybe like a very brief comment on why does this work. So the reason why this works, I guess this kind of calls back to a line of work on what's called kernel random matrices, right? So a kernel random matrix is just a matrix where in the ijth entry, I'm applying a function to the inner product between two vectors on the sphere. So kernel random matrix is just a matrix where the ijth entry is equal to some function of zi, zj. These are iid over the sphere in d dimensions. Kernel random matrices have been, they're a classic object of study, and they're really, really well understood when the dimension is fixed relative to n. So when the dimension is fixed, we understand these really well, and usually what happens is that the spectrum of M as a matrix is related to the spectrum of F as a function over the sphere. And when the dimension is growing relative to n, and also when this function depends on d and n, things get much more complicated and the classical theory doesn't apply, but still you more or less expect that the spectrum of M is related to the spectrum of F. Okay, and that's basically what's happening for us here, even though we can't use any of the classical tools to prove this. If you look at the ith entry of j, right, this is the indicator that ui and uj exceeds our threshold tau. And what you can do is you can write this in its polynomial approximation, right? This is going to be something like p plus some dependence on the linear term ui dot uj plus a different dependence on the quadratic term, ui uj squared, etc. Okay? But if you look only at the constant and linear term, you'll see that A is basically P times the all ones matrix plus lambda 1 u transpose, where this is just the n by d matrix whose ith row is just ui, right? So this is actually our embedding. Okay, plus something which I'm going to call delta, and this corresponds to the rest of the spectrum. So the quote-unquote linear approximation to A is just a constant plus the embedding that we wanted, right? And you could then show that basically the top d plus 1 eigenvectors of A are something like the all ones vector and the embedding that we wanted if you can show that this has small enough spectral norm. And we just basically do this by hand using the trace method. So that's how the proof works. I'm kind of optimistic that maybe you could prove things about other kernel random matrices in the same way. Of course, with the trace method, we didn't. Like, there's a lot that we could have done to try to squeeze some extra juice out of this and, you know, address these kind of egregious polylogarithmic factors that we did up there. But we opted to keep proofs clean. Okay, so this is the thing. I mean, our analysis of the spectral norm here, I think, is something that could be improved. Okay, do I have like 2 minutes to say some open questions? Okay. Okay, open. Okay, so the most obvious open question, this is actually a 0 in my handwriting, is, you know, like, what about the sharp thresholds, right? So as I said, I think our analysis here was a little bit loose. And furthermore, I think that if you really want to get to the constant average degree regime, you might have to use some fancier spectral algorithms, like ones that use the non-backtracking matrix or something like that, right? So those are all things that we did not do, but I think they should be doable here, and then you could understand what's happening exactly at the thresholds. Okay, another question which I implied before already, but I'll just recap it here. So what about algorithms when the dimension exceeds n times the binary entropy of P, and mu is not too large? And then, okay, also maybe an obvious question, but I think a really interesting one, is what if you deviate from this very, very simple two-community mixture of Gaussians, right? So other mixtures of Gaussians. Two directions which you could move is you could go to non-identity covariance. Or you could ask for a mixture of k more than 2 Gaussians. For the latter problem, we have already, in the Gaussian case, a very, very rich information computation landscape, right? I think it is pretty interesting to see what happens and how that will interact with the information loss that we get from subsampling. And in the non-identity covariance case, I mean, I'm not that optimistic about the performance of the spectral algorithm if you have poorly conditioned Gaussians, but I think it could be pretty exciting if we could actually come up with algorithms that address this case, because my suspicion is that people who are running spectral clustering in practice often are actually dealing with poorly conditioned mixtures. Like the feature space should not be well conditioned. If we can do something here algorithmically, I guess it seems plausible to me that this could actually give guidance to what's going on in practice, although you should always be careful before saying something like that on a recorded video. Okay, so that's all I had to say.